we're ready to put it into action. So I'm going to turn the page. Let's look at 13.2. We see a same situation, different equations. And so the most important use of E is at this thing that's called continuously compounding. I'm actually even going to write that. I'm going to put it right up here. If something is continuously compounding, that means it's constantly growing at a consistent factor, right? So all of our exponentials that we've looked at, we're always drawing graphs that show exponential growth, something like this. And we may take snapshots and say, hey, we know the population here to start with, and then we know the population 10 years later, and what is that growth per year? But in reality, when people are studying nature or science, when you're looking at medicine or really all of this stuff, it's happening continuously all the time in these itty-bitty little increments. So it's not just that the population grows at the beginning of the year or the end of the year. It's growing and changing every single day along the way. So continuously compounding gives us this idea that it's making these itty-bitty little changes all along the way. So this colony of insects starts off with 9,000, and I see both equations have the same starting value to represent that 9,000 insects when it is first studied. And when we look at these two factors and their exponents, we see some interesting differences. This one tells us that it's keeping the full 100% every year, and it's adding 2% to its population. And it looks like not every year, every month. So it keeps its 100% and it adds 2% each month. And so we can find that nice equation, that formula we would use, so we can find it every single month. This one, though, uses base E. And you'll notice that it has the same starting value. This time the factor is just E. And then the exponent has the amount that it's growing by. Now notice here it was 100% plus 2% more. Here it's just the 2% that it's growing by. So here is where that growth factor is. And then the t as we had before. So two big changes in these equations that we have. Same starting. T is still in both exponents. But one of them has the factor in the normal box where we see the factor. And our other one, I shouldn't even write the word factor there because we don't even want to confuse it with the other growth factor. Our factor is E, and here is the rate that it's adding, that it's changing by. It asks us to use technology to find these, and so when I'm looking for multiple input values here with T, alright, if you have a graphing calculator, you can certainly use your Y1 and your Y2 to input these in, but I know most of you are working from home now and are maybe going to be looking at something like a Desmos instead. So I'm going to do this on a Desmos screen. In the first one, I'm going to type in our first equation, 9 times 1.02, and using the caret symbol, remember shift 6 is the caret, I'm going to raise it to the x exponent. All right, I know our equation says t, but I'm going to use the x. Now I just want to have that one graphed first, and if I scroll back a little bit, I can see where this is starting to show up, but I need some x values that are going to go from 6 to 100 because that's what our chart is looking for. So I'm going to zoom way back until I can see from 0 to 100 on my x scale. There's a nice way to look at it. So I have from 0 to 100. And I'm going to use a dot. If I hover over here, I can hold down a cursor and I can move it from place to place, and I can see what the x and y coordinates are. So looking at my book side by side, I see that we also, we're looking for some different values. So the first one is when t is 6. So I want to move until I see where t is 6. And I see that that is 10.135. I'm going to click over and enter that into my workbook here. 10.135. And I'm going to do the same thing for all of these down here, 12, 24, 48, and 100. 12, 11.414, 24, 14.476, 48, 'Oh, it's so touchy. So we're just going to keep on filling in all of these values all the way down. Oops. 23.284. And we'll find each of those values. Now we also want to compare it to a second equation, 9 times e, and I'm just typing in the letter e using my keyboard, and it knows that e is a value. I'm going to raise that up to 0.02x as my exponent. When I see that, I see it has graphed this blue line, and it's almost exactly on top of the red one. But up here it starts to get a little bit farther apart. So the farther we go, the more farther apart it will be. I'm going to turn off my red one so I can just trace my blue one. So I just did that by clicking the radio button over here, and so it just has the blue graph on. And so I'm going to also enter in each of the values when x equals 6. Now again, we could actually put in values that'll go a little bit faster and easier. If I need my x to equal 6, I can use that button right there and find that it's 10.147. How about an input of 12? Hover over that dot. And we see that our values are incredibly close to what we had our first time through. Not exactly the same, slight differences, and actually as we go farther and farther along, we're going to find that they actually get more and more different from each other, more and more separated. So I can start using each of these values, 23.505. And last but not least, it wanted it up to 100. And so I start to see, as I then have those values back in my workbook, that as we went along, they started off pretty close to each other, and they just got farther and farther apart, and this one, our second one, was always just a smidge higher than what we were seeing with our first one. We're going to also see, so that's what we might notice about the two models. They start off very similar, but slowly grow more apart. As, and in this case it's t, as time increases. And we can even say something like q of t was larger. So I'm going to use the greater than symbol. Q of t was greater than p of t. Is going to get farther and farther apart the longer it goes. Question 3 tells us we have a pair of equations representing populations in thousands of 4 insect colonies in the research lab. Each one of them has an initial population of 10,000, and they're all growing exponentially. it asks us to graph each pair of functions on the same coordinate plane. Now you can use Desmos, since you already have a Chromebook out and you're watching this video. So you could graph these on Desmos and see what they're looking like, but it gives us a window to look at. So I'm just going to use my calculator and graph each pair of functions on the same coordinate grid. And to see what we notice about the graph of the equation using E and the counterpart without E, make a couple observations. I'm going to do this just for colony 1. I already have some ideas from our first example that we've done of what I might be finding. Putting in my 2 equations. Sorry, that glare was pretty rough. So I put in my first colony 1 equation, my second colony 1 equation in the same coordinate grid, and it asks me to have my x's from 0 to 50 and my y's from 0 to 80. So I'm going to go to my window, my x's from 0 to 50, my y's from 0 to 80. This way we're all looking at the same kind of window of information. And here's my first graph. In black. And this one you can see a little bit better. My second graph in red, as it gets higher and higher, see how they start getting a little bit far apart. So I'm going to put a red dot on that one so I remember that one's the one graphed in red. And it starts off right on top of it, and then it kind of starts to go a little bit separate like that. I'm going to hit pause, and I'm going to draw the same picture for each of my other colonies. Please do the same with me. Hit pause on this video, and let's see what happens as we go forward. Alright, so I hit pause, and I have all of mine now graphed into my equation. So I have my 2 equations for colony 2, my 2 equations for colony 3, and my 2 equations for colony 4. I'm going to graph them all at the same time and kind of show you that drawing of what they're looking like, although you're probably seeing the same thing. Although sometimes it's nice to see it in color like this. So here's these 2 that are coming in right now. And you can see that they are almost right on top of each other, but the second one at the end goes a little bit higher. Here come the next 2. Almost completely identical. And my last 2 for colony 4. They're like right on top of each other. You can see the color just coming right on top. So it seems like colony 1 is the farthest apart as we go along. Colony 2 gets a little bit far apart, and then colony 3 and 4 are almost identical, almost right on top of each other. So when I look at some things that I notice, they all start very similarly. Almost on top of each other. So each pair starts off almost on top of each other. And something that I started to notice is that the farther along we went in the colonies, the more they stayed on top of each other. So the thing that I noticed that changes between these, this one is looking like it's adding a 5% to it, so that's a rate of 5% that it's adding. This one's adding 3%. This one's adding 1%. I'm getting this right here from the rate that we have in both cases. And this one's adding just 0.5%, 0.5%. So another thing that I noticed is the higher the percent change in population, in this case, the higher that percent change that we have, the farther apart the graphs as T gets larger. So the difference between the 5% colony here is more drastic than the difference between the 0.5% colony. The higher the percent change in population, the farther apart the graphs get as we get to higher numbers of T.